So how do you use that? How is that useful? Why is it useful? It's useful when you come to ask the question. Remember, the reason you're doing this is you're trying to reduce the dimensionality of your data. So you start out with a high-dimensional, d-dimensional space, and you want to pick a smaller number of dimensions, m, where m would be a lot smaller than d. So which dimensions, which eigenvectors do you pick, and how many of them do you pick? And you can get the answer just by looking at the eigenvalues. Remember, each eigenvalue tells you exactly how much variance you're going to capture along that eigenvector. And the sum of all eigenvalues turns out to be the same quantity as the total variance in your system along all the dimensions. So in PCA, you're trying to preserve as much variance as possible. So what you should do is you should pick the eigenvectors with the biggest eigenvalues, because they are the ones that are going to capture the most variance in your data. So a typical way to do that is you sort the eigenvalues in decreasing order from the biggest to the smallest, and then you look at the cumulative sum. So you take lambda 1 plus lambda 2, lambda 1, lambda 2, lambda 3, and so on. If you plot the cumulative sum, it's going to look like that, right? And we can divide it by the total variance in the system. So the sum of all eigenvalues is going to be just the total amount of variance, and the sum of the first m eigenvalues is divided by that is what proportion of the variance, what percentage of the variance do you capture by taking just the first m eigenvalues, just the first m eigenvectors as your new dimensions of space. So it's going to be a graph like that. It's going to be converging to 1, so asymptoting to 1. In practice, you pick some arbitrary threshold. You say, I want to capture 90% of the variance or 95% of the variance in my data. And then, based on that, you just look for the value of m that gets you over 90% of the total variance. And that will typically be a relatively small number, because this graph, it will ramp up very quickly and then sort of take a long, long time to get to 1. It'll get to 1 when you have used all the eigenvectors, and there's going to be d of them. So if you want 100% of the variance, you cannot possibly reduce the dimensionality of the data. The dimensionality is going to come out at d. Usually, unless your data really, really lies on a linear subspace, which doesn't happen. Okay, so you can use this to pick how many dimensions you have in your data. Now, in all honesty, so it sounds nice and fancy. I'm capturing 90% of the variance in my data, but why is 90 a good number? Well, why not 87? Why not 93? At some level, 90 is completely out of a hat, right? So you just pick it because you like it or because it looks like a nice number. There is nothing magical around 90%. It's just, to us humans, it seems to make sense. So people pick those numbers. But ultimately, you should pick whatever works best. In some cases, people forget about that and they just ignore that and use the same scree plots, the ones that you used for k-means, right? So instead of looking at the cumulative sum, just plot the eigenvalues. The first one's going to be the biggest, and smaller, 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 and then you look for the point, or for the inflection point, for the point where you seem to have an elbow, where the eigenvalues were decreasing very quickly and then they stop decreasing. That's another useful, sensible way to determine how many dimensions to pick.